specific homework questions. They can kind of be just things in general, but I'm happy to kind of take a few minutes here and talk about these things that you worked on your own before we move on to the next stuff. Gabby?
Can you give number
9? Sure. So 9 says we have 3 pi over 7 radians. It says to convert from radians to degrees and then round your answer to the nearest hundredth. So the conversion to go from radians to degrees is 180 over pi. So usually the way I like to do this is I just cancel the pi's by hand, and then I'll just go to my graphing calculator and do 3 divided by 7 times 180, and that would be 77.14. Cool there. Cool. Anybody else? Or who's next? Landon? Okay. So this is I think 22 is the most difficult of these story problems. Just because mostly it's sneaky on how you actually have to do the solving. So it says 2 toy racetracks form concentric circles. We'll pause here and just kind of clarify what we mean by concentric. What we mean by concentric is like you have 2 circles where they share the same center. So something like that. Each track is divided into 15 identical sections. So I'm just going to kind of draw one of those sections because I don't think I can probably draw 15 identical sections. But if they're all exactly the same, all I really need to be able to see is one of them. If the inside car travels 1.2 centimeters less than the outer car on each piece of track, so I'm going to identify this as like S1 and this as S2, and then I can say that S1 is S2 minus 1.2. Okay with that? How much bigger is the radius of the outside track? So I'll call that R2, than the radius of the inside track. I'll call that one R1. Set up 2 equations using the arc length formula, and then use substitution to solve. Round your answer to the nearest hundredth. So probably the natural thing to do is to say, okay, I know the arc length formula is this, and the theta I'm going to find, I guess, will probably be in degrees. So I'm going to do the conversion to radians there. So the first order of business I need to do is I need to figure out this angle theta. Now it's nice that it's the same theta for each arc since that the circles are concentric. So I know that if this is split into 15 identical sections, I have 360 degrees in the entire circle. And I'm be splitting that into 15 pizza slices. So 360 divided by 15 is 20 something or another's. $24 degrees. So I can fill that in. The problem, at least on the surface, appears to be, though, that I have 1, 2, 3, 4 variables, but only 2 equations, which you should remember from last year that you can't just solve for 4 variables. I need 4 equations, right? Well, here's the sneaky part, is it's not actually, I don't actually need to solve for R1 and R2 separately, because it just asks for how much bigger is the radius of the outside track compared to the inside track. So it would be enough to just solve for R2 minus R1. So that's really what I'm going to shoot for. So what I'm going to do is I'm going to subtract these 2 equations together. So I'm going to subtract equation 1 from equation 2. When I do that, on the left side I have S2 minus S1, and on the right side I have R2 times 24 pi over 180 minus R1 times 24 pi over 180. Is that okay? I notice that both of those terms have a factor of 24 pi over 180. So I'll just factor that out. And that's going to get the R2 minus R1 by itself. I also notice that because I know S1 is equal to S2 minus 1.2, I can rearrange that by subtracting S1 from both sides and adding 1.2 to both sides. I know that S2 minus S1 is 1.2. So I can replace the S2 minus S1 with 1.2. So then I can just multiply both sides by the reciprocal. Oops, that's supposed to be 24 pi, not 2 pi. And that would do it. So that would be about 2.86 centimeters. Now this is more difficult than something I'd expect you guys to be able to do on a quiz or a test or whatever. But sneaky, of course. I can't see your face. Oh, Victoria. 19? Sure. So 19 says, again, 2 concentric circles are cut by the same angle. Okay. So I'm going to just grab this same picture here. The radius of the smaller circle is 4.3, and the cut arc measures 5.2. So we know R1 is 4.3, and S1 is 5.2. If the radius of the larger circle is 5.2, what is the length of the cut arc? Round our answer to the nearest hundredth. You good with my initial setup here? The picture that I've drawn, and then I just recorded the information for the labels from the story problem. That's all okay? So here's the trick, is that I know that like S1 is going to equal R1 times theta. And I know that S2 is going to equal R2 times the same theta, because the angle is the same in both situations, right? So I'm going to use that first two pieces of information to solve for theta, and then use that answer in the other equation. So 1.21. Victoria, are you okay there?
Yeah.
Okay. So I have that. So I can take this and then this together. And I get about 6.29. And these were inches, I think, was the unit there. Does that make sense as to what I did? So the big observation was realizing that it was going to be the same theta for both arc length equations. So I can use the theta from the little arc to find the length of the big arc.
Okay, so the cut arc, like, is always going to be like an S?
Yes. So when we say cut arc, that's like the arc formed by that central angle. So it's just the same thing as the S in our arc length formula. Lily?
Is it possible to do 23?
So this is a dimensional analysis problem, very similar to like the one that we did in the example. So it says Danny is riding a bike that has 22-inch diameter wheels. If he can ride at 14 miles per hour, how many revolutions per minute are his tires making? So we want to convert 14 miles per hour to some revolutions per minute. Okay with that plan? Okay. So I'm going to start by setting this up like I would a dimensional analysis problem. So I'm going to write 14 miles per hour as 14 miles over 1 hour. And then I want to convert this into revolutions per minute. So the first thing I'll do is do the time conversion. So I want to convert this from being per hour to being per minute. So I know that 1 hour has 60 minutes. And I remember that the units have to line up diagonal, so that's how I know that the 1 hour is going to go in the numerator. So far, so good. So when we multiply there, the hours are going to cancel, and now I'm in miles per minute. What we need to do then is we need to convert miles to revolutions. And the key there is that I know that 1 revolution is equal to 1 circumference. So the circumference of a circle is pi times the diameter. So in this case, that would just be 22 pi. And that's inches. But currently my unit is in miles. So before I can do that conversion, I got to convert miles to inches. So let's think here. I know that 1 mile, I don't know how many inches it is, but I know it's 5,280 feet. And I know then that 1 foot is 12 inches. So when I do those multiplications, the miles cancel and the feet cancel. Now I'm left in inches per minute. And then my last step here is that I know that there's 22 pi inches in 1 revolution. So that'll get me now to my unit is revolutions per minute. So I've done the unit cancellation. Now I just have to figure out the number. Is that okay so far, Lily? You can ask me if you can't read something. You know, like I get it. My penmanship is sometimes less than spectacular. All right. So the way I like to do this is I'm just going to do all the multiplications on the top. So I have 14, and I'm not going to bother with the times ones because multiplying by 1 doesn't really do anything. And then on the bottom, I'm going to put a big parenthesis. So I did the division symbol and then a parenthesis. And I'm going to skip the ones, but then I have 60 and then times 22 pi. So that should be about 213.9 revolutions per minute. Well, it wants to the nearest thousandth, so 213.904. Hi, how are you doing?
How are you?
You're welcome. Maria Caton, this is for you. I'm assuming you probably knew this was coming. Mm-hmm. Here you go. You're welcome. Lily, are you happy with what we did there? Yeah. Okay. Any follow-up before we move on to the next person? Okay. Who's next? Maria. No. Yes.
Can you explain like the chart?
Yeah. So all you're doing on 13 through 18 is you're just using the appropriate arc length formula.
Like the problems above.
Yeah, you just have to make sure that you're using the correct formula depending on the theta that you're given. So like, for example, if I'm doing 13, I notice that my theta, or my angle, is given to me in radians. So I use that formula. And so I just would type like 1.2 times 2.1 into my calculator and blammo! That would be my answer. So just basically using one of the two formulas over and over again. And I think there's just the one problem. I think 16 is the only one where you're asked to find the angle, in which case you'd have like two possible answers. You could give it in degrees or radians. It doesn't really matter there. Does that feel okay? So it's really just kind of using either one of those two formulas, just doing like little algebras with it, but it's nothing complicated. It just looks complicated, but it's just like, here's like 5 or whatever, 6 questions that are all kind of the same-ish, and the compact way of kind of formulating them. You know what I mean? But each line is like its own separate question in the table. Is that,
Yeah.
That's what you needed? Okay. Of course. Did we make it into the sine, cosine, tangent stuff? Did you guys get that far? Is that a no? Okay. All righty. So, what should we do today then? Did you guys watch the lesson for 2.2? We just didn't get to the homework, or get that far into the homework, but we watched it. Okay. And you remember doing similar things in your geometry class last year, I hope, or 2 years ago? Using sine and cosine and tangent to like solve a right triangle and stuff. Remember SOHCAHTOA? What those things stood for? Do you want to review one of those real quick? Sure. Sure. Okay. So let's say we have this right triangle here, and we're asked to solve this triangle. That would mean we'd want to find the side for AC, find the value for angle A, and find the value for angle C. So far, so good. Doesn't really matter which one we start to find first. They're all accessible. What do you guys think here? Which one would you want to start with? To find angle A, you say? Okay, let's do that then. So if I'm looking for angle A, I know something about the opposite side and the adjacent side. So which trig function should I use in this case? Tangent, right? Because I know that tangent is opposite over adjacent. So I would say that tangent of A is equal to the opposite over adjacent. Everybody so far so good? Now if we're solving for angle A, we need to get rid of that tangent out in front. How do we get rid of the tangent in front? We use tangent inverse, right? If we're solving for an angle, you're always going to be using the inverse trig function at some point. If you're looking for a side length, you'll just be using the regular ones. Is everybody okay there? Does this ring some bells from your geometry course? I know that was a long time ago, or potentially a long time ago. So let's go ahead and type this into our calculator and get the value for angle A. What do I have to be careful about when typing this into our calculator? The mode. So typically on a question like this, how would we report our angles? In degrees or in radians? Degrees. Yeah. So the first thing I'm going to do before I do anything into my calculator is I'm going to press the mode button and make sure that I'm in degree mode. So go ahead and check that if you're following along. We are. So I'm going to just exit out of there by pressing second in mode. And then to get the tan inverse, you'll notice in blue above tangent is the tan inverse command. So I'll just do tan inverse of 6/5. So that's about 59.19 degrees. Everybody's okay with that? Now, as a direct consequence, angle C is going to be easy to find. Why is that? As a direct consequence, angle C is going to be easy to find. Why? Gabby, did you have something? You're mumbling something at the same time Landon asked the question. Because we already know angle A. And what else do we know? Well, we also know angle B, right? What's angle B? 90. How many degrees are there in a triangle? 180. So angle C then just has to be 180 minus 90 minus 50.15 or 19. So we can get angle C without having to do really any trigonometry, right? We don't need to use sine, cosine, or tangent at all. Oops. 50.19. So that's 39.81 degrees. So far, so good. How should we find AC? We now have a couple of different ways to do that. What'd you say? You could use the Pythagorean theorem, and that would really be the best of our options, because to do the Pythagorean theorem, we know that a squared plus b squared equals c squared. That's the Pythagorean theorem. And the thing to remember here is that when we say A and B, those are the legs of the triangle, and C is the hypotenuse. So we know both of the two legs exactly. Those were given values, which means that this will have the only rounding going on will be at the very end, which is nice. So 5 squared plus 6 squared is 61. And then we'd square root both sides to get just C. So that would be about 7.81. Landon?
Sean, could you just restate how you got 5 squared and 6 squared?
So the A and B in the Pythagorean theorem are the legs of the triangle. But again, remember the hypotenuse has to be the C. It doesn't matter which leg is A and which leg is B. That doesn't really matter. The hypotenuse must be the value for C. Is this kind of ringing some bells? What do you think? Do one more? Okay. Okay. So this one's a little bit different in that instead of given two side lengths, I'm given one side and one angle. So this is the other situation that you could run into. You can't ever have a situation where you're given two angles. There's just not enough information to be able to come up with the side lengths from that. So you'll either be given two side lengths or a side and an angle. Okay, one of these three, angle C, side AB and side AC, is trivially easy to come up with. Which one is that? Angle C. Why? We have the other two angles in the triangle, right? So we can say that angle C is 180 minus 90 minus 36 which is 54 degrees. Yeah. Double check my arithmetic there. So that's nice. Okay. Now let's solve for a side length. Does it matter which side length we try to solve for first? No, it doesn't matter. So let's pick a side length that we want to solve for. Which one do you guys want to do? AB or AC? AB, great. So now let's pick an angle that we're going to use. We can either use the 54 or the 36. It doesn't really matter, but we just need to pick one. The 36. Okay. So relative to the 36, AB is the adjacent side. And the 4, the other angle or the other side we know, is the opposite side. So the trig function I need to choose in this case is tangent. So I would say that tan 36 equals opposite over adjacent. Is everybody okay with that? So remember, the angle measure is always the part that goes inside the trig function, right? We do sine, cosine, and tangent on angle measures. And we do sine inverse, cosine inverse, and tan inverse on ratios of side lengths, like a fraction. Okay, so to get AB by itself, it's in the denominator of the fraction, right? So I would multiply both sides by AB. Everybody's okay there? And then I'll divide both sides by tan 36. Remember, tan 36 is just a number, right? That's something we can type into our calculator. So if I have AB times tan 36, that's just one number, right? So I can just divide the tan 36 over to the other side. You could convert it into a decimal at any point and work with the decimal, but you have to be careful about the rounding, right? If you round too much too early and you round several times during your calculation, each time you do a step, you can end up with a really inaccurate answer by the end. That's why I'm going to kind of just call it tan 36 until I'm ready to put it into my calculator. So we'll do 4 divided by tan 36. And so that's 5.51. Is everybody okay there? Now to find AC, what should I do? That's the last piece for us, right? Landon? Okay. Somebody else with an idea then? It's okay to be wrong. Right? Like nobody has all the right answers all the time. Even if you're volunteering, something that is incorrect, that's good. I'm happy to do that because what that does is it kind of tells me where our head's at. We can talk about why something doesn't work, which is often more productive than just having the right answer all the time. Right? It's because we get to address some kind of misconception, talk about, okay, why that wouldn't work, which is usually really helpful for you guys. Landon?
So does the 5.5 now, use it to the a squared plus b squared?
Great. So you can use the Pythagorean Theorem because you have 2 of the 3 side lengths in the right triangle. What's going to be the downside of that? Yeah, it's you're using a rounded answer. Right? So now we have like 2 roundings going on. You're going to have the rounded 5.51 and then the rounding again at the end to write our final answer. Now, in a case like this, we're rounding to 2 decimal places. It's probably not going to matter. But if you're trying to land like a rocket on the moon, it might make a difference there, right? Is there a way that we could do this where we only are rounding our final answer? So I want to be clear here. The Pythagorean theorem will be fine, right? But there is a better way of doing this problem, and it's only better because it requires less rounding than using the Pythagorean theorem here. We can do this without having to use the 5.5. So, Ahmad, what's up? Well, again, if you use the 54 and you use... So, okay. So let's, you could use 54. And if we're looking for AC, and we know the 4, in this case, the 4 relative to the 54 is the adjacent. This is the hypotenuse. So the trig function I'd want to use in this case would be cosine. Could you have also used 36 again? Sure. But we didn't. We said 54. So cosine is the adjacent over hypotenuse. Oops, let's use AC though. That's what I've been using. Uh-oh, hi Siri. And then we can repeat kind of the same steps that we did on the previous problem, right? Notice here, there's no rounding going on until the final step, right? I'm not using the 5.51 that we had to round earlier, which makes this answer like a little bit more accurate, but probably not enough so that you would make any difference on like a test or a quiz or something. Like it'll be fine to have used the Pythagorean theorem. Would have been no big deal at all. But I like to talk about that because, well, depending on what you're doing, sometimes rounding really matters and sometimes it doesn't, right? So it should come up to be about 6.81. And just to illustrate, if we did the Pythagorean theorem, I still would end up at 6.81, but you notice I get a slightly bigger value or whatever out there in the later decimal places, which almost anything that we would do in our real life ain't going to make any bit of a difference. But if you're doing something like rather complicated or it needs to be very precise, it might make a difference. I think I remember hearing one story where they're trying to land a probe on Mars. I don't remember which one it was, but like somebody, the number that they were using for pi, like they just cut it off or rounded it at like the 10th decimal place, and they figured out that that was what caused their probe to like not land where it was supposed to or whatever, is because like that turned out to be the thing that made the difference. Was like, oh, we needed more digits of pi or whatever in our calculation to do something really like, oh my gosh, that's the level of precision you're looking at to do something like this. So like, for us, no, it doesn't matter, but like it matters sometimes. Of course. What do you guys think? You feel okay on this solving a triangle business here? Again, it's something we all did in our geometry class. Whether we remember that from 2 years ago is another question. But we have done this at least preliminary. I think right triangle trigonometry is a geometry topic everybody deals with. Okie doke. Okay. We're going to pause here. I'd like, well, do you guys have some more questions on things that you want to talk about? Debbie?
Can you do like an X, which radius of like the like yeah.
Yeah, so all these letters represent, so S is an arc length. So like this is, that distance there is our S. R is a radius. So for example, that distance is an R, or this distance is an R. And then the theta is the angle measure. And that's, this equation is for theta in radians. So for example, if the radius is, 9 and the arc length is 12 or whatever, and you want to find theta, 12 is equal to 9 times theta. And that's it. You're just plugging the numbers into the right spots and then solving for the appropriate variable. Or if we were given, say, like, the radius is 5 and theta is, like 2.1 radians or whatever. Just type in our calculator. Is that cool? Seems okay? Yeah, Rami?
Would you still be able to can you mess with that formula and plug in other things? Like I think number 2 would be impossible like that.
So like the next question there was about just converting, right? So if I want to go degrees to radians, my conversion factor is pi over 180. If I want to go radians to degrees, it's 180 over pi. And that's basically all you need. So if I have 116 degrees, I just multiply that by pi over 180, and that'll spit out my answer in radians. And to answer your question more specifically, kind of you could use that formula, but it's like a lot of overkill to do it. That's like how we derived that conversion factors. We kind of used that arc length formula to some extent, but that's kind of a lot of work versus just remembering that conversion factor. But that's kind of all, that's it. It's just using the appropriate conversion factor. And the way that I remember it, just like any other unit conversion, like if I want to convert inches into centimeters. I have 10 inches. I have to multiply it by 1 inch, then has to go in the denominator. So if I have 116 degrees, the degrees have to go in the denominator, so I know the 180 is on the bottom, and the pi radians is on the top. Give me an answer in radians. If I was given something in radians, I'd want to multiply it by 180 over pi radians, so that the radians would cancel, and I'd be in degrees. So it should be easy to remember like which way the fraction goes, because it's going to work just like your unit conversion does, like in your science class in chemistry when you did the unit conversions there, whatever. So like that's like 355. Does that feel okay, Ron? I messed up. Told Emilio. I don't know what I did. My apologies. Just completely the wrong named. That's my fault. Okay, so I heard, can you do one and then do something and then 25?
Yeah.
Oh, from the homework?
Yeah.
Sure. So 25, we gave like, a triangle, and we give some values for A, B, and C. I'm just going to fill in those values here. And then it asks for the 6 trig functions for this theta. So relative to this theta, this side is the opposite, this side is the adjacent, and this side is the hypotenuse, right? And I know sine theta is opposite over hypotenuse. I know cosine is adjacent over hypotenuse. I know tangent is opposite over adjacent. And then the 3 new ones, cosecant is just the reciprocal of sine, so it's hypotenuse over opposite. Secant is the reciprocal of cosine, so it's hypotenuse over adjacent. And cotangent is the reciprocal of tangent, so that's adjacent over opposite. So that's all we're doing, it's just writing the ratios, basically.